Here, inside this refrigerator, at a temperature just a tick above absolute zero, isolated from the rest of the universe, is a quantum computer.
Quantum computing is an emerging branch of computer science that uses the power of quantum science. This makes quantum computers exponentially more powerful than conventional computers in certain areas. Conventional computers store and interpret all data through binary bits, encoded as either a 0 or a 1. Quantum computers use qubits that are far more dynamic, with the potential to express and interpret data at unprecedented scale and speed. As quantum computing advances, new possibilities in data processing, storage, and security are imminent.
This nascent technology embodies the promise of the future and has the potential to revolutionize our lives with its turbocharged computation. But quantum computers aren't the next generation of supercomputers. They're something else entirely. And before we can even begin to talk about their potential applications, we need to understand the fundamental physics that drives the theory of quantum computing. We'll need to dive into another dimension, smaller and more alien than anything we intuitively understand: the subatomic world of quantum mechanics. In the 1980s, one of the most important physicists of the 20th century encountered a major roadblock. Richard Feynman was hungry for a window into the quantum universe. But quantum systems, by nature, are fragile, and the information they hold hides from us. Because Feynman couldn't directly observe quantum events, he wanted to design a simulation. It quickly became clear that his computer wasn't up to the task. As he added particles to the quantum systems he was modeling, the cost of computation began to rise exponentially. Feynman concluded that classical computers just can't scale up fast enough to keep pace with the growing complexity of quantum calculations. Then he had a breakthrough. What if he could design a tool made up of quantum elements itself? This instrument would operate according to the laws of quantum physics, making it the perfect way to probe the mysteries of the quantum realm. The idea of the quantum computer was born, and by dreaming it up, Feynman had started to build a bridge between quantum physics and computer science.
Key features of quantum computers. Qubits. Qubits are the fundamental units of quantum information. Unlike classical bits, which are either in a state of 0 or 1, qubits can exist in a superposition of both 0 and 1 states simultaneously. This property allows quantum computers to perform parallel computations on a vast number of possibilities at the same time. Superposition. Superposition is a quantum phenomenon that enables qubits to exist in multiple states at once. This property is harnessed to explore multiple solutions to a problem simultaneously, potentially leading to a significant speedup in certain types of computations. Entanglement. Entanglement is a quantum phenomenon where qubits become correlated with each other in such a way that the state of one qubit is directly related to the state of another, even if they are physically separated. Entanglement enables the creation of quantum states with unique properties that can be exploited for quantum information processing. Quantum gates. Quantum computers use quantum gates to manipulate qubits and perform computations. Quantum gates operate based on the principles of quantum mechanics and can perform operations like creating superpositions, entangling qubits, and implementing quantum algorithms. Quantum parallelism. Quantum computers leverage the principles of superposition and entanglement to explore multiple solutions to a problem simultaneously. This quantum parallelism can lead to exponential speedup for certain algorithms compared to classical counterparts. Quantum algorithms. Quantum algorithms, such as Shor's algorithm and Grover's algorithm, exploit quantum parallelism to solve specific problems more efficiently than classical algorithms. Shor's algorithm, for example, can factor large numbers exponentially faster than the best-known classical algorithms. How quantum computers process information differently. Superposition. While classical bits can be in a state of 0 or 1, qubits can exist in a superposition of both states simultaneously. This allows quantum computers to explore multiple possibilities in parallel, providing a potential speedup for certain computations. Entanglement. Entanglement allows qubits to be correlated in ways that classical bits cannot. Changes to the state of one qubit instantly affect the state of its entangled partner, enabling the creation of unique quantum states with correlations that classical systems cannot replicate. Quantum parallelism. Quantum computers can process a large number of possibilities simultaneously, thanks to superposition and entanglement. This capability is particularly advantageous for certain optimization problems, searching algorithms, and factorization tasks. Quantum speedup. Quantum algorithms, when applied to specific problems, can provide exponential speedup compared to the best-known classical algorithms. This potential for speedup has implications for cryptography, optimization, and other fields. Quantum uncertainty. Quantum computers can leverage the inherent uncertainty in quantum systems to perform probabilistic computations. Quantum algorithms can exploit this uncertainty to find solutions to problems with a higher probability of success than classical algorithms. It's important to note that building and maintaining stable quantum computers is a significant technical challenge due to issues such as quantum decoherence, loss of quantum information, and error correction. As of my last knowledge update in January 2022, practical and scalable quantum computers are still in the early stages of development, with ongoing research and advancements in the field of quantum computing.
Quantum computers are based on a completely different model of how the world works. Quantum computers use atomic quantum states to run computation. Data is held in qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin and a magnetic field, or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be just one of those. It can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, for example, by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So, as long as it is unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a quantum computer's superpower. Classical computers' bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. Another surprising property of the quantum computers is the entanglement effect. What this means is that the data held in qubits is affected by data held in other qubits instantaneously, no matter how far they are apart. When measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. From a computing perspective, this implies that data is recorded and stored in a different way, through non-binary qubits of information rather than binary bits, reflecting the multiplicity of states in the quantum world. This multiplicity can enable faster and lower-cost calculation for combinatoric arithmetic and is a true game changer. Quantum computers can do many of the things that classical computers can. However, in addition, they do one big thing classical computers cannot: perform combinatorics calculations quickly. Google's quantum computer, for example, has recently completed a calculation in less than 4 minutes that would take the world's most powerful classical computer 10,000 years to complete. The following 5 domains will be disrupted by the quantum computers. First, artificial intelligence. Quantum computing opens up new opportunities in AI, which often involves the combinatoric processing of very large quantities of data in order to make better predictions and decisions. A growing research field in quantum machine learning identifies ways that quantum algorithms can enable faster AI. The current limitations on the technology and software make quantum artificial general intelligence a fairly remote possibility, but it certainly makes thinking machines more than a subject for science fiction. Second, drug discovery. Chemical and biological engineering involve the discovery and manipulation of molecules. Doing so involves the motion and interaction of subatomic particles. In other words, it involves quantum mechanics. As molecules get more complex, the number of possible configurations grows exponentially. It becomes a combinatorics calculation suitable for a quantum computer. With the emerging feasibility of quantum simulations, which helps predict the properties of new molecules, engineers will be able to consider molecule configurations that would otherwise be challenging to model. This ability means that quantum computers will play an important role in accelerating current efforts in materials discovery and drug development. Third, cybersecurity. Combinatorics have been central to encryption for over 1,000 years. Al-Khalal's 8th century book of cryptographic messages looked at permutations and combinations of words. Today's encryption is still built on combinatorics, emphasizing the assumption that combinatoric calculations are essentially unmanageable. With quantum computing, however, cracking encryption becomes much easier, which poses a threat to data security. A new industry is growing that helps companies prepare for upcoming vulnerabilities in their cybersecurity. Fourth, complex manufacturing. Quantum computers can be used in taking large manufacturing datasets on operational failures and translating them to combinatoric challenges that can identify which part of a complex manufacturing process contributed to incidents of product failure. For products like microchips, where this production process can have thousands of steps, quantum can help reduce costly failures. Fifth, financial services. Finance was one of the earliest domains to embrace big data, and much of the science behind the pricing of complex assets, such as stock options, involves combinatoric calculation. When financial firms price derivatives, they usually apply a highly compute-intensive calculation known as a Monte Carlo simulation, which makes projections based on simulated market movements. Computing speed has long been a source of advantage in financial markets, where hedge funds build complex infrastructure to get millisecond advantages in getting price information. Quantum computing will definitely help financial industry to make the next big leap forward.
In classical computers, the fundamental block is called bit, while in quantum computers, the bit is replaced with qubit or quantum bit. What's the difference? Classically, the data is characterized by a bit. A bit is a basic unit of classical information. It can take two possible values, either 0 or 1. In contrast to this, quantum bit is the basic unit of quantum information. Qubit can take many values at the same time in the form of 0 or 1 or superposition of both 0 and 1. This right here gives us the foundation of why quantum computers need so much more attention. Speedup is the answer. In the same cycle, when classical computers deal with two states, quantum computers deal with many states, which means much more data.
The benefits of interference in quantum computing. In this video, we'll be discussing how the phenomenon of interference, which is a fundamental principle of quantum mechanics, can be used to perform powerful computations that are not possible with classical computers. One of the key benefits of interference in quantum computing is its ability to perform certain calculations much faster than classical computers. This is because quantum computers can perform multiple calculations at the same time, using the principle of superposition. Superposition means that a quantum bit, or qubit, can exist in multiple states at once, allowing for multiple calculations to be performed simultaneously. Another benefit of interference in quantum computing is its ability to solve problems that are considered intractable for classical computers. For example, quantum computers can use the principle of quantum entanglement to perform certain types of data analysis that are not possible with classical computers. This could have a wide range of applications, such as in cryptography, drug discovery, and even climate modeling. Interference in quantum computing also has the potential to revolutionize the field of machine learning. By using quantum algorithms, such as quantum neural networks, quantum computers can perform machine learning tasks much faster and more efficiently than classical computers. In conclusion, interference in quantum computing has the potential to revolutionize the way we perform calculations and solve problems. With faster processing speeds and the ability to solve previously intractable problems, quantum computing has the potential to change the way we live.
Quantum technologies promise to revolutionize many critical industries, from logistics to medicine. And thanks to that promise, companies and countries are investing big. According to a report by global consulting firm McKinsey & Company, in 2022, a record $2.35 billion was invested in quantum technology startups. And in April 2023, India announced it was going to become the 7th nation with a dedicated quantum mission, behind the US, Austria, France, Finland, Canada, and China. But what's going on behind the hype? Well, these are still nascent technologies based on the relatively new field of quantum science. Quantum computers will be able to solve some problems much faster than classical computers, but they won't be great for everything. And the ultimate impact of quantum technologies could be something we haven't even thought of yet. There are dangers to be aware of too. Quantum computers could make our current encryption methods obsolete, and the rise of these technologies could lead to a quantum divide between those who can access them and those who can't. A future with quantum technologies looks exciting, but we need to prepare ourselves for both its potential and its risks.